We're going to talk about the equivalent conditions of continuous linear operators today. So to do that, first recall what we define as boundedness. So that E be a subset of the topological vector space. And in section 1.6, we define that it is bounded in a topology if for every neighborhood of 0, there exists a number t, a real number t, such that the set E is containing SV for every S larger than t. Then we say it is bounded. But in a metrizable space, we have a metric, so that's write as D bounded. And the bounded is very easy. It's just the familiar notion that we have. So we just have dx0 is smaller than some positive number for every x in a set E. Then it is bounded. And you have to be cautious about these two notions because they are not actually equivalent. So we can have D-bounded set that are not tau bounded. So, for example, we construct a metric in the theorem 1.24. So in theorem 1.24, from a countable local base, we construct a metric, which is dxy equal to f of x minus y. And you remember that this set or this metric will be the whole space whenever the value is larger than 1. So in this case, the pole B1, which is all the points smaller than 1, we can take equal here, so it will simply be a whole space. So it means that the notion above, dx is smaller than m for some m larger than 1, will be the whole space. Which means that for every subset of a topological vector space, E is bounded in this sense. It's bounded, which is not very useful, right, if everything is bounded. And another example we have is, so let's mark this as 1. So for a Banach space, so say X with a norm with the induced metric D. So this metric will induce a topology that is compatible with the topology induced by the norm, right? So in this case, we can define a new metric. This will also be a metric, so that be another metric. And in this case, this will always be bounded by 1, actually strictly bounded by 1 for every xy in the space, which also means that every set is bounded, so every subset is bounded. So you have to be very careful about this. But still, the both B1 over n in the metric space is still a local base. This does not change. Forms a base. So just to clarify, whenever we say something is bounded, we always mean it is bounded in the topology. So there's no confusion. So let's prove a little lemma here. So every Cauchy sequence is bounded. Every Cauchy sequence. Let's call it Xn is bounded. So the proof is very easy. So follow from the definition of a Cauchy sequence in section 1.25. So a sequence is Cauchy in the topological sense. Is Cauchy in tau. Means that for every neighborhood of 0, here exists a natural number such that xm minus xm lies inside this neighborhood for nm larger than n. So this is a definition. So from this definition, we fix m as the large n, then we will have xn lies inside xn plus v. So for every n larger than n. Let's finish the proof. Oh, actually, we have to do one more step. What we do here is we again, to prove that bounding, we have to use the definition of the topological boundedness, right? So pick. So for any neighborhood, be a neighborhood of 0. What we do is we choose V, a neighborhood of 0, such that V plus V is inside W. Then because every single point is bounded, exists T such as Xn lies inside T V. Then what we have now is, so this V actually will be chosen as the same one. So we will do this first. We'll do this first, then we'll choose this V here. So for this V, we'll choose this integer n here. So we actually do this in the reverse order. So after we do this, what we do is we just estimate these. So xn lies inside the neighborhood of xn plus v, which is inside tv plus v. And if we choose t to be larger than 1, this will also be inside tv plus tv. And by the property we demand here, this will be inside tw. This proves that xn from big N to infinity is bounded. And because there's only finite points left, x1 up to xn minus 1 are also bounded. So the whole sequence is bounded. And this will be useful later. So just as before in the metric space or in the Euclidean space, the convergence sequence, or more generally, the Cauchy sequence are bounded. And another fact that we proved before is that if E is bounded, it will imply that its closure is also bounded. So next, another fact is that any non-trivial subspace is not bounded. So we just pick an X that is not zero. Then we denote the set X, 2X, all the way to NX into the infinity by this E. And this will not be bounded. And the reason is very easy. So for every neighborhood V, neighborhood of 0, there exists, say, M, such that MX is not in V. So just for a fixed neighborhood. Then it will not contain O, because whenever say we enlarge it by T times, then T times MX will not be in the set. So this will never contain a whole set. So E is not bounded. And this implies that any non-trivial subspace not equal to 0 is not bounded. And next, we'll prove a little lemma for the main result of this video. So it says that E be a subset of a topological vector space, then E is bounded if and only if any sequence in the set E and alpha n is a sequence such that it converges to 0, then alpha n x n converges to 0. So from the boundedness, so if E is bounded, so by definition, pick a neighborhood of 0, exists T such that E is containing TV. And this will imply that T every point xn will be inside the set. Now because alpha n converges to 0, so we can find, say, n such that alpha n times t is smaller than 1. And what this will do for us is that we actually need for every n larger than n. So this implies that alpha n xn will lie inside alpha n times tv. Because alpha n t is smaller than 1, this will be inside V. And because this is true for any neighborhood, this implies that the sequence converges to 0. Now, suppose E is not bounded. It's not bounded. So there exists a neighborhood of 0 such that TV does not contain the set E for every t larger than 0. And now we just pick a sequence in a way such that pick xn in E such that xn is not contained in, say, nv. Thus, this implies that O does not contain in V, which implies that this does not converge to 0. So this proves the theorem. Now comes the boundedness of the linear transformation or the linear function or the linear operators. So first thing you want to notice is that we do not apply the usual notation of boundedness to the function. So by which means that in usual, like on the real axis or in the complex analysis, we'll say that a function from, say, R to itself is bounded if f of x is smaller than some positive number and for every x in the real number. But this is obviously not true because, let's say, for any linear operator and any vector such as it is non-trivial, and say it is also in Rn, okay? And this will not be 0. So we can just enlarge this freely. So we just multiply by alpha, and this will simply become alpha times this value, and this will be arbitrarily large as alpha goes to infinity. So the definition we apply here is bounded operator or bounded linear transformation operator. Means that for every bounded set, the image of this bounded set is also bounded. So under this definition, we can derive some property of the linear operators. So theorem 1.32, we have that x and y are two topological vector spaces, and lambda is a linear operator from x to y, so linear. And now we have 4 properties. So A says that lambda is continuous. B says that lambda is bounded. C says that if we have a sequence converges to 0, then the image of the sequence, lambda x, is bounded. D, again, if a sequence converges to 0, that will implies the image of the sequence also converges to 0. So in general, for general topological vector space, we have A implies B implies C. If further X is metrizable, then we also have the implication C to D to A, which actually implies that boundedness is equivalent to continuity. So let's do a quick remark here. If X is not metrizable, there does exist here exists lambda that is bounded but not continuous. And this an example in exercise 13 in this chapter. So the general idea is that we just look at the same space, so x to x, but with different topology. So for example, we can have y here with the usual strong topology, and if we equip with the x with the weak topology or the weak star topology, this will the identity map will actually be discontinuous, but the boundedness will be actually equivalent. So this will give us an example. And the point here is that this space, the topological vector space equipped with the weak topology, is actually not a space with countable base. So we only have uncountable base. So this is proven in B of the exercise 13 as well. Okay, let's prove the theorem. So first we have continuous to bounded. And it's very easy. So we just pick a neighborhood in Y. Then by the continuity of lambda at 0, because lambda 0 is 0, there exists a neighborhood in X such that lambda of V is inside W. So now if E is a bounded set of X, that is bounded. And now we choose the multiplier with respect to this V that we just have here. So exists T such that E is contained in TV. Now we just do the calculation. So lambda E is contained in lambda TV. Then by continuity we have it is contained in T lambda V, which again is in lambda W. So this proves that it is bounded. Now we have bounded to X and converges to 0 implies that the image is bounded. The image is bounded. So this is actually proven in the very beginning of this video. We prove that every Cauchy sequence is bounded. So by the boundedness of the operator, so because convergent sequence is bounded, so the image is also bounded by the definition of the boundedness of an operator. So we finished the first part. Now we assume that the domain is metrizable. So from now, let X be metrizable topological space with a metric D. Now we want to prove from C implies that image is bounded to D, which says that if a sequence converges to 0, then the image also converges to 0. So to prove this part, we recall the previous theorem we proved, theorem 1.28, which says that if we have a sequence that converges to 0, then there exists a sequence that goes to infinity, such that multiplying these two together still converges to 0. Which also implies that the sequence is bounded. So the sequence is bounded. Now, this immediately implies that xn is equal to gamma n inverse lambda gamma n xn. Because this part is bounded, this implies that the whole thing goes to 0 as n goes to infinity. So we finish C to D. Finally, to prove D, if xn converges to 0 implies image also converges to 0, then it is continuous. The operator is continuous. The lambda is continuous. So to prove this, we use contradiction. So if lambda is not continuous, and again we pick a neighborhood W, neighborhood of 0, such that W contains inverse image of W contains no neighborhood of X, of 0 in X. Now, from this, we also use the fact that X has countable base, as it is metrizable. Then we can find a sequence xn such that xn converges to 0, but lambda n is not in W. And we can do this very easy. Recall that we can have a local base that is nested. So remember in the theorem we proved the metrizability. We can have a local base with the following property. So essentially it is a nested neighborhoods of X that is also a local base. So what we do, we just pick n be a member of Vn minus Vn minus 1 and the inverse image of W. Then we will find the sequence as xn will eventually converge to 0. So this proves the theorem. So the very important fact about linear operator in metrizable spaces is that boundedness is equivalent to continuity. Metrizable, then continuity is the same as boundedness. Of course, it's for linear operator. And we'll talk about semi-norms and local convexity next time.